Hola, and bienvenidos a la clase de precalculus.
Yeah, what she said.
Okay.
So today, yes, we are recording this on a Friday afternoon, children, at 5 o'clock in the afternoon. See how much we love you?
We heart you.
Yeah, we do, really. I know. We like torturing you too, but anyway, we love you. So today we are going to conclude the material that is on the test. This is the last section, and it is on section 5.3, Applications of Exponential Functions. After this section, we do a lot of cool things with exponential functions and their inverses, so get ready. Now, the easiest way to talk about exponential functions is to look at the most basic thing we know about, and that is how interest is computed. So many of you are destined to eventually maybe take a business class, so you really need to understand interest. We have compound interest and continuous compound interest. We'll first look at compound interest. You've got to understand the formula and know the formulas will not be given to you on the test. All right, compound interest. The P stands for the principal. That is what you invest.
The amount of money that you put in the bank.
Yeah.
That's your principal.
It's called the principal, not Dr. Counsel. She's the principal too, but she's not the principal we're talking about. Next is the interest rate. Now, interest rate, if we say 5%, you need to convert that to 0.05 to go into the problem. N is the number of times per year. Okay, so if we are talking quarterly, that means four times per year. And T is the number of years. Okay, so once you know what each one of those represents, it's relatively easy to set up your problems. Now, when you do the ET problems on this, we have to see the setup of the equation like we're going to show you. So first of all, what we have here is we are going to invest $9,000.
Oh, wait. How much money did I put in the bank? $9,000.
So that is our P, principal. P for put in the bank. At 4% interest, we have to convert that as our interest rate. R, and 4% is 0.04. Compounded annually. Now, N is the number of times per year. So if we're compounding it annually.
If you want to have a party annually, how many times per year do you hold the party? One time.
So N is 1. Notice how we are identifying each variable and the number that represents it in the problem. How much is in the account at the end of 5 years? So how long are we going to invest our money? A time of 5 years. Again, notice that T is in terms of years. All right, so using our compound interest formula, we would write A of 5, because that's our how long, equals 9,000, parentheses, 1 plus 0.04 over 1 to the 1 times 5. Okay? Now, that is our formula. This is what we need to see on your paper, and our answer is, oopsie, why don't we write
I'm going to remove this. I'm going to shrink it down. What we've done is we're going to show you how you do these on your calculator, but just with a screenshot, okay? So when we do these, basically, this is what it's going to look like. What I did was I put in the calculator, oh goodness, okay, it's got to go away sometime. All right, what I did was I went to the graph screen and I actually graphed this function, 9,000 times 1 plus 0.04 over 1 raised to the n power, x power, okay? And that's what f1 of x is. See, there's the f1 of x. That's what I typed in.
But you have 1.04. That's not 1 plus 0.04 over 1.
Believe it or not, it did it for me. However, 1 plus 0.04 is 1.04.
Oh, yeah, yeah.
So that's where it comes from. Okay, then if I type in my calculator screen f1 of x, or f1 of 5, it gives me the function at 5. So it actually plugs in 5 into this equation for me, which is kind of neat. But we want you to set it up for us. And this is money, so hopefully you don't live in a world where you get half pennies. That would really stink.
Right.
So this is actually going to round down.
Let's see. We're going to invest, and
we'll round up.
No, I think it'll round to 87 cents because the bank is not going to give you. They're not going to give you. If you owe the bank money, they're going to round it up. But if you get money from them, they're going to round it down. So it's going to be 87 cents. Now, if you were paying back interest, paying back a loan,
It's going to round up.
Then you would pay 88 cents instead of 87 because that's just the way they do it.
Okay, that's approximately.
Approximately.
All right.
Good.
Okay. All right.
Okay, example 2. Determine that the amount that a $5,000 investment over 10 years, there's your number of years, at an annual interest rate of 4.8%. And notice that A, B, C, and D are for different numbers of times per year. So let's write down the things that are consistent in the problem. The things that are consistent in the problem is that our principal is 5,000. Our rate is 0.048. Our number of years, N, is
change.
10. Our
N is going to change.
N is going to change.
Based
T,
on each one.
Yeah, and T is 10. All right, so annually, we would write here that N equals 1.
Oops. N equals 1.
Mm-hmm. And so our formula, we also want to come up with our general formula. Let's write.
I'm going to write it down here.
Yeah.
All right, so I have A of T equals 5,000 times 1 plus, because we're increasing our stuff, 0.048 over N. We don't know what that is, times N to the T. Now we know what T is, so I'm going to come on in,
10.
and I'm going to go ahead and...
Actually, what I think we should do is I think we should leave this in terms of T.
Okay.
And write this time NT. And excuse me, 10N. Because we know what...
Well, T... Okay. Anyway, so we have A to the 10 of 10 equals 5,000.
10N, but our T is 10. Okay, got it. Okay.
1 plus 0.048 divided by N.
Oh, yeah.
10N.
Sorry. I was already a step ahead. Sorry. Okie dokie. And so now we're going to let N equal 1. So
Okay,
it's a matter of just showing us the equation. And our equation here is, there's our 5,000
times 1 plus 0.048 over 1. 1 is our N, raised to the 10 times 1.
And really what we would want to see over here is A of 1 equals.
This is what I typed into the calculator. So
Yeah, in the
A
calculator.
of 10 equals this, where N is 1.
Oh,
okay?
yeah, that's right.
So $7,990.66.
Okay, good. Now let's look at quarterly. Quarterly is 4 times a year. So the only thing that changes in the problem is everywhere you had a 1 becomes a 4 because that represents the number of times per year.
This one changed. Not every place you have a 1. This is always going to be a 1, all right?
Oh,
because
yeah,
we're talking
sorry.
about 100%.
I meant 1 for N.
This one right here is going to change to a 4, and this one right here is going to change to a 4.
Yeah.
All right, so we end up getting A of 10 when we have a quarterly rate is $8,057.31. Remember, we're at a bank, not a place that will like you to give them money. Oh, they want your money.
Yeah.
Yeah. Okay. For monthly, how many months are in a year? 12. So N equals 12. So every time we had N is now a 12. So A of 10 is 8,072, and I know 63 cents. It looks gross, but it's going to round down. And then daily. Well, how many days are in a year? Well, some of you
this
smart
year
people,
there's 366 because
okay,
it's a leap year.
Technically, it's supposed to be 5.25. However, banks don't like to give you more money than you already are going to get. So when you're talking about daily, N equals 365. Okay, so don't think too hard into it. So here we go. What we've got is 5,000 times 1 plus. We've got 365 in the denominator now. So our interest rate is now, or our amount of interest, or whatever we get, whatever we have in our bank after a year, 10 years, is $8,080.11.
Now, what's important to recognize here is we invested $5,000. So over 10 years, you can see that each of these accounts basically gave us around a $3,000 increase in the amount that we invested.
If you notice, if it compounds more often, you get more money.
Yep.
So what a compound does is it takes the money that you have, like the interest, and it puts it into as your principal. Okay, that's what compounding is. So that's what's really cool about it. So now you're getting interest on your interest here, whereas here you're not as often.
You're just getting once a year.
Yeah, this one they're only putting the interest in once a year. This one they're putting it in once a day. All right.
Okay, so this one, $7,000 is invested at 5% annual interest, compounded monthly.
So that means that our N
Number of times per year
is 12 because there are 12 months in a year.
Now, notice that we're not told how long it is being invested for. That's because the question is, when will the investment be worth $8,500? So what we've got to do is, first of all, let's come up with our function in terms of t, because that's what we're looking for. A of t is 7,000 times 1 plus 0.05 over 12, closing parentheses to the 12t. That lets us see that what we are actually looking for is how long. We don't know the time. It is a function of time. The other thing we know is that a of t, for some length of time, we want it to equal 8,500. Now, if you look at these two equations, doesn't it make sense that if a of t equals the 7,000 blah 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 and it equals 8,500, couldn't we set the two equal to each other? Why, yes, we could. And the equation that we would solve is not something you know how to solve yet, except we can look at it on the graphing calculator and look at the two functions.
So I graphed a of t, the first one, and f of 1 of x, and I graphed a t equals 8,500 and f2 of x, and now I have my curve and my line. I know it looks kind of like a line, but that's where how it looks that zoomed out. And this is from, you can't see it very well, but this is from 0 to 8 on the x-axis and from 7,000 to 9,000 on the y-axis. Now, why did I pick 7,000? Well, if you look at your original equation, you're starting out with $7,000. Wouldn't it make sense that your money's going to grow from that point? So it doesn't make sense to start higher than that, but it doesn't make very much sense to start very much lower than that because you're going to be growing. This is increasing your money. So what I did was I pressed menu, analyze graph, intersection, and this is my point that I got. So since x is the independent variable and time is what we would look at, the time that it takes to get $85,000 is approximately $8,500 is approximately 3.9 years,
which month-wise is about 47 months. And why would we be interested in that? Because we're compounding it monthly, so we might. Yeah.
So 3 years times 12, and then 0.9. Let's see, that's about.
9 is 3/4 of a year. 9/10 of a year.
9/10 of a year.
9/10 of a year,
which is about 10 months ish.
Mm-hmm.
You would have to compare it. So
yeah.
Anyway, all right. So here are the first ET problems. Go to section 5.3 in your textbook and work 1, 16, and 23 and show your setup, please.
Especially since we've given you odd ones where you can check answers.
Okay. The next set of problems that we're going to look at, if you invest $100, so we're not as wealthy this time, at 100% annual interest, wow, that's intense. 100% annual interest, I'd like that. What is the maximum possible value of the investment after 1 year? So remember we were talking about how if you compound it more often, you get more money. So we're going to look at some different choices. Copy and complete the table and answer the question. Okay, so basically we have it $100. We've got 1 plus 100%. Remember it's 100%, so R equals 1. And we're going to change that. So I went into the calculator and I did a table. Oops. Let me move it over a little bit. Basically, I graphed this function and in f of 1 of x, and then I have this connected to this function here. And I was able to just type in our stuff here.
Mm-hmm.
So that way I didn't have to do the same equation over and over again in the calculator screen. So annually, I would get $200. That makes sense because in 1 year, I'm going to double my money. So $200 is right. If I compound it quarterly, then I would have $244.14.
Mm-hmm.
Okay, if I compound it monthly, so that's 12 times a year, I would have $261.30. If I compounded it daily, I would have $271.45. If I compounded it hourly, oh goodness, I would have $271.81. And if I compounded it every second, I would have $271.82. Well, 82
Yeah,
cents.
2 cents, 82.
Okay. All right. So if you notice, this is a exponential type function. Okay, and the more I get, the size isn't really changing all that much, and that's because you've got this. You're dividing by n here, so it's not getting that much bigger. Anyway.
Yeah, and what's kind of cool is this actually, if you let n get big, this quantity here, now we have multiplied by 100. So if we just took our initial investment of $1, this would actually get very close to this number we like to call E. E is named in honor of a famous mathematician whose last name was Euler, E-U-L-E-R. And the number E is something that shows up in so many different mathematical applications. Just like pi is 3.14159, blah, 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 blah. Well, and the symbol pi represents that number. The symbol E represents that number. Now, when you go to use E on your calculator, we'll show you in a few minutes, but you do not type in the letter E. There is a special button that has actually got the function. But what's really cool is as you go towards infinity, this number, 1 plus 1 over n to the n, gets very close to that number there.
So if you notice, every second is a lot, right?
Yeah.
Well, if you keep going closer and closer to microseconds and milliseconds, like the smallest amount of time, instantaneous, it's called continuous, okay? And if I compound continuously, I'm going to use E, because that's as fast as you can possibly do it.
Yep, so that's the important thing. So now let's do one where we're compounding continuously. So let's look at our principal, $3,500, interest rate, 3%.
So 0.03.
And continuously means we're going to use E.
So N equals E.
And we actually have a special formula. Compound continuous interest, the formula is A equals P E to the RT.
Because remember, this stuff is all getting close to this. So
yeah. So notice there's no N's in here. That's because the E is really accounting for that. Okay?
Right, and then we're looking for at the end of 4 years. So our T equals 4 years. All right, P is the same as principal, so I've got 3,500 times E, which is our special number, to the R, which is 0.03, times 4.
And this represents A of 4. And we just plunk that on our calculator, and we get the, oopsie.
Well, okay,
Yeah.
What we're going to get is, I'm going to move this a little bit. All right, we've got 3,500 times E. Notice how it's bold? That means we're using the right one. To the 3.03, and that's what we get. So we get, the dollars, $3,946.23. Okay, but how do I find this E button, you say? Well, here's how you do it. Do you see this button that's red? That's the E raised to the power of whatever. Okay, so press 3,500 times, press that button, and then press 0.03 times 4, enter, and that's how you do it.
Yeah, you don't even have to use the caret
Right
because that red button there is already set up for E to some power, E to the X. So,
okay. So for compound interest problems, go ahead and look at 11.
Continuous.
Continuously compound,
Yes.
yeah. Continuous compound interest problems. Look at 11, 22, and 35. And show your setup. Okay.
Okay, so we're going to talk about exponential growth, and if you remember, in the last section we dealt with graphs of exponential growth as well as exponential decay. Well, they have other versions of the formula that we gave you. Notice that up there we have f of x equals p times a to the x. That looks a lot like our exponentials that we used, but now we can talk about that a as 1 plus r, where the r is the interest rate. And
not the interest rate, the growth rate.
The growth rate, excuse me. I'm thinking about money right now. And so that is, and the 1 is there because what you're talking about is the amount that you initially have plus a percentage of the amount that you initially have. So that's why they just combine it in the 1 plus r. So example 6, the population of Tokyo in the year 2000 was about 26.4 million. Notice our units here, okay? It's projected to increase at a rate of approximately 0.19%. Now notice that is 0.19%. So the rate is not 0.19 but 0.0019. So you have to pay attention, read carefully. Write the function that gives the population of Tokyo in year X, where X corresponds to 2000.
Okay, so we're talking about millions. And it's giving, and it says gives the population of Tokyo, I would assume in millions. So
A of X.
F of X, since that's what we're doing,
yeah,
equals the principal. Well, what's the principal amount? Well, 26.4. Since we're saying millions, we can just go ahead and say this is going to be in millions and use 26.4 times 1 plus our rate, which is 0.0019 to the X.
And we want to recognize that that really would be 26.4 times 1.0019 to the X.
And that way you don't have to add in.
And there it is. That's your function. And now we could say 10 years from now, what will the population of Tokyo be? And that's what's really neat about that.
Okay, a newly formed lake is stocked with 900 fish. All right, so that's the current amount of fish in the lake. After 6 months, biologists estimate that there are 1,710 fish in the lake. Assuming the fish population grows exponentially, how many fish will there be after 24 months?
Okay, there are several things to think about. First thing we have to do is come up with our equations. So that is going to be f of x, okay, p of x. Population is 900. And right now, f of x equals 900, a to the x.
So we don't know what r is because it doesn't tell us how fast it's growing. And that's what we're trying to figure out.
Let's remember that our 1 plus r, that came from our a. If you remember, look back on the previous page. But here's what we do know. Yeah, so we want to recognize that that is a to the 6th. We also know that f of 6, a to the x, f of 6 is 1,710. Now, how can we use that? We do not know the growth rate. We're not told in this problem, and that's why we need to understand that a is 1 plus r. Now that we have a growth rate when x is 6, we can put a 6 right there where the x was. And now, how would you solve this? Just think, we're solving for the a, so we need to divide by the 900 on both sides. And it turns out that when you do 1,710 divided by 900, you get 1.9. And 1.9 equals a to the 6. Now, how would we solve for a? Well, we would raise each side to the 1/6. And if I raise that side, I can raise the left side to the 1/6. And so we get a to be 1.9 to the 1/6. And you could do on your calculator, figure out what that is. Now that is a. By the way, if we wanted, since we know that a is equal to 1 plus r, okay.
All right, so.
Well, okay, go ahead.
Well, okay, since we know that a is 1.9 to the 1/6 power, we could actually solve for r. We could do 1 plus r equals 1.9 to the 1/6 power.
Yeah, and so if you were asked in a problem like this to find the growth rate, well, how would you do that? Well, you would do r equals 1.9 to the 1/6 and then subtract 1. Notice that it does not become 0.9 to the 1/6. You have to actually do the 1.9 to the 1/6 and then subtract the 1. And that could be useful in some problem where you're actually asked to find the growth rate. Okay, so continuing with the other issues of this problem, we now were asked to find in 24 months. So it's just a matter of f of 24 equals 900 times 1.9 to the 1/6 to the 24.
Notice that this is all talking about months, and that's why we don't have to change the stuff to 2 years, okay? Because this is all talking about months.
Well, especially, yeah, because we did the 0.6, the 6 there.
6 months.
If we had wanted to talk about this in years and you wanted to have the 24 months, you would have had to put 2 here where you have the 24,
And
which
0.5.
means 0.5 where you had the 6. So you have to really pay attention to your units. That's really super important.
All right, so we have here all this lovely math. 1.9 to the 1/6. You can use a caret button for that. And then close parentheses, caret button. There we go. And you get that. So it's approximately, we're talking about fish here, so we don't want half a fish. So 11,729 fish, approximately.
Yep.
All right. So, I'm going to write fish.
Yeah, that's good. Units.
For units.
Yeah.
Okay. Exponential decay. Each day, 15% of the chlorine evaporates in a swimming pool.
Well, look at the formula up there. Notice that with growth, exponential growth, it was a 1 plus R, and with decay, it's 1 minus R. Again, another important detail when you're thinking about problems and being asked to do something to find a growth rate. Okay.
This is an exponential decay, so it's going down. All right, so the 15% of the chlorine in a swimming pool evaporates. So this is a percent, this is a rate. So our R is going to be 0.15. After how many days will 60% of the chlorine have evaporated?
Well, this has 2 parts. The first thing we need to do is write this formula out. F of x equals P times 1 minus R to the x. All right? We aren't told what our initial amount, so let's just assume we are going to put in, let's talk about 1 gallon. Okay, just put a 1 there. And then parentheses, 1 minus 0.15 to the x. So that gives our formula for the amount of chlorine present as 0.85 to the x. Okay, now that's the first side of this problem, is that represents the amount of chlorine that is present. Now the second part of the problem says, after how many days will 60% of it have evaporated? Well, we have to think about this. I know you've done this in chemistry. If we talk about 60% that is evaporated, we need to convert that to how much is present. If 60% has evaporated, then 40% is present. And we know that is represented by 0.4. And that is the other equation we're going to look at, is that f of x is 0.4. And once again, an Algebra 1 concept, if f of x is 0.85 to the x and f of x is 0.4, can't we set them equal to each other?
So, what I did here, with the calculator, is I used the store function. I did 0.85 to the x store. You do control and then var, and that's a store function of f of x, f1 of x, and then it says done. And then I did that for f of 2, so 0.4 store in f of 2, and done. And then I said solve f1 of x equals f2 of x, and then I said solve for x. And then it gives me 5.638, which is, we're talking about days. And since we're talking about days, decimals are okay. So x is approximately 5.638 days.
And that's really kind of interesting, because that means that if you just go throw a certain amount of chlorine into the pool, in 5.638 days, it would be evaporated down to only 40%.
Keep chlorine in the pool. All right, so go to section 5.3 and do number 43 and 49 and show your setup.
Okay, radioactive decay. So in the problem, some of the ones you'll see in the book, and other times, you might see something called plutonium-210. Well, that 210 is not a number that shows up in the problem. It's just identifying a certain type of chemical, so please don't get thrown off by numbers. Like in this problem, we're getting ready to talk about iodine 131. That 131 is not a number in the problem.
It's talking about the number of electrons in the valence. It's the number of electrons in the valence shell.
That's very good for you. I had horrible chemistry experience, hated it. Anyway, radioactive decay. So if you notice, we're talking about, look at that 0.5. That actually is going to be talking about a half-life that's in the problem. All right, so here we go.
And a half-life is basically the amount of time it takes for half of the amount to decay. So, like, let's say you have 5 grams of something. Well, you want half of that to decay, so you would have 0.25 grams, okay?
2.5.
2.5 grams.
Yeah, so you're talking about how long it takes that thing to break down to half of its original amount.
Yeah.
Okay? All right, here we go. The isotope iodine 131 is used to treat some types of thyroid disease. Iodine 131 decays exponentially with a half-life of 8.02 days. If the quantity of iodine 131 is administered to a patient, how long will it take for 99% of it to decay.
So remember, we're talking about something decaying half of it at a time. So after one day, half of it will have decayed. Then the next day, another half of whatever was left will decay, etc. So it's going to get farther and farther down.
But it actually takes 8.02 days for it to decay to half.
Okay, so not,
Yeah.
Anyway, so f of x equals p is the initial amount of substance. Well, we don't know how much they're giving this person, so let's just say 1. All right, times 0.5.
0.5.
0.0.
0.5. Ugh, I can't read.
Okay.
Sorry.
And x is the same time of units. We don't know what that is yet. That's what we're solving for. Over the half-life, which is 8.02 days. Okay. And then we're talking about we want 99% to decay. So that means...
99.
Oops. We want 1% left.
Just like the last one.
Or present.
How much present? The last example.
Okay, which equals 0.01. So it's asking us, well, when is f of x equal to 0.01? Because 1% of 1 is 0.01, okay? So, yeah, so that's why we're nicely using 1.
I could use any amount.
But you have to multiply by the percent.
Yeah, you get the same result with any amount, but you'd have to adjust throughout the problem.
So you're going to set these two functions equal to each other. And I did it the same way I did in the previous problem. I set this equal to f1 of x, this equal to f2 of x, and then I said solve. f1 of x equals f2 of x equals comma x, and then there we go. So it will take 53.284 days, okay, for the isotope to decay to 99%. Okay, so go to section 5.3 in your textbook and work number 51. And set up the equation, please. All right, to confirm that you have indeed watched this video, email your teacher by 8 a.m. the day you have class with the following information. 1 new thing you learned. And I hope it's something good, because there's a lot of new stuff in here. 1 good question. 2 old skills that are important to recall. And don't forget to bring your entrance ticket to class. Thank you.
Bye-bye.
Adios.